in last class we started talking about memory, right? So, almost cover. So, I need to tell maybe another 10-15 minutes. So, I will tell you later. So, today we will start a new topic is something called instruction pipelining. Book is directly you can see that is our favorite book, that is Hemeshar. Okay, his book is very easy. Okay, with compared to if you compare the other books like his okay. So, this book is much easier. It's like you are reading stories. Okay. So, that is why this book is taken. Okay. We will be going through stories here today. It's not much in computer architecture or organization. After the end of the class, I think you will see many of those things. Okay. So, pipelining is widely used in modern processor. Okay. Pipelinings improve the system performance in terms of throughput. Okay. So, what is throughput? You must have studied in other class. Throughput is the number of job completed per unit time. Okay. So, how many maths you can do in a in 1 hour, that can be considered as throughput of you. Okay. So, here is actually number of instruction executed per unit time is called the throughput. So, number of instruction executed by a processor per unit time, that is called throughput. Okay. Yeah, pipeline organization required sophisticated hardware. So, this slide as I told ki nothing is there in this slide, right. So, what is throughput? As you know that number of instruction executed per unit time. So, this is 0 slide, okay. Nothing is there, no information. Okay. So, next is main objective is that actually I said earlier also that we want a computer that we invest minimum money, but we will get the faster processor. Okay. So, you want that program executed in fastest way. Okay. For that what can be done is we can use the faster circuit for each part like ALU and all other circuits. Otherwise, what we can do it multiple instruction we can execute parallelly. Okay. So, that is the arrange the hardware so that more than one operation can be performed at the same time. So, parallelly we can do it, otherwise we can have faster circuit. So, yeah, even though in hardware we are going to study pipelining. So, basically we will do multiple instruction will be executed parallelly. Okay. But for execution of single instruction will remain same time. To execute single instruction it will take let us say 1 hour, but if you execute multiple instruction that will take lesser time. It is not if I want to execute 10 instruction it will not take 10 hours, it will take lesser time, but for each instruction it will take 1 hour. So, I will say with one simple example that it will be very much clear here. Say this is there are 4 guys here and they have they need to do this thing to wash the cloth. So, this is washing unit, then there is a dryer and then there is fold. Okay. That means pressing the cloth. Okay. And for each one it takes first one washer takes 30 minutes, dryer takes 40 minutes and folder takes 20 minutes. So, each guy will take 30, 40, 20, so 1.5 hour, right. So, therefore, if we complete the 4, so it will take 1.5 into 4, so it will take 6 hours, but this can be reduced. So, that is something called pipeline. How can you reduce? Can we reduce? Okay. So, here we go. This is very simple. Actually, first guy initially he took and complete it, then second guy again hit start and complete, and third guy again start and complete and start and complete. So, that is why I said it 6 hours. Now, if you do little different, okay, how? This is we have 3 different units here. So, first guy completed and then he now moves to second one was the dryer. So, now is that you can see the washer is free. So, that could be used for the could be used by the second guy So, second guy, that is B, started using this part, and first guy, when he is doing folding, he is using folding part, and then second guy, what he can do it, he can start drying, but third guy, he can start washing. So, then if you see that fourth, this time unit, that all three units are going parallelly, earlier it was not happening. So, this is nothing but the pipeline. Okay. So, like if you have a assembly line car, wherever that car produce, there are many parts. So, some guys will do the chassis, some guy will do painting and so on. So, instead of completion one and then other team will work, so it can be done that all team are working parallelly in the similar fashion here. There is no contradiction. So, therefore, what time, how much time it will take? So, it is reduced to 3.5 hours. But if you carefully observe that for each guy it is taking exactly the 1.5 hours. So, he started from here and then exactly 30, 40 plus 40, 20, that is all, that is pipeline. So, now we will go into computer pipeline. Yeah, same thing, I stayed here. There are some assumption is actually no one should stop in between, life will be very smooth, okay, like each will take, there are some assumption, each will take, it will be good if each unit takes the equal time. So, that is the pipeline does not help latency of a single task, as I said the single task will take exactly the same time. So, pipeline rate limited by the slowest pipeline stage, I do not like reading this so slide, okay. So, multiple tasks operating simultaneously using different resources and so on. So, you can read those things, okay. But main idea is like each task will take exactly the same latency, latency means starting and then ending. This is something called turnaround time, when you start the work and then when you end, okay. So, I can say that for BTech courses turnaround time is 4 years, for some lucky guy he can take 5 years. Okay. So, because why lucky? He like NIT Rourkela very much. Okay. It's so environment is so hot in summer and then so cold in winter. Okay. So, turnaround time is 4 years. So, latency is actually 4 years. Okay. But in there is some problem, then he can take more time. So, similarly in pipeline situation also, if for some reason if pipeline is stalled, okay. So, obviously it will take much time, that we will see. So, these are the, you can see this one, you can read this one, right. Yeah, now we will come. I told is instruction execution has different stage or phases, right. So, once I said ki instruction fetch and then is execution, okay. So, fetching means it will take out the instruction from the main memory and place to the processor and then it will execute, that is simplest way, okay. So, fetching and then executing, but I said it is not that, it will fetch, then what will happen, if you remember initial class I said it will fetch the instruction and then there is something called instruction decoder, right. So, it will decode the instruction. What is the task of the instruction decoder? So, it will tell what is this instruction, what the instruction is, what it needs to be, let us say addition. So, addition is the task. So, that is the operation needs to be performed, okay. And for that it needs 2 operand and so on. So, one of the operand might be in memory, again in the main memory. So, that also has to be brought. So, therefore, it is not only the 2 parts, there are other parts also, the other phases. But before going into much detail, so you take one more example where life is so simple, like it has, let us say you assume it has 2 phases, but you have already seen that in earlier example it had 3 phases like wash, dryer and the fold. So, here you consider the 2 phases. So, if there are 2 phases and if instruction executes sequentially, so what will happen? So, fetch, execute, fetch execute and fetch execute. Instead of that, if we use the pipeline, so this is the example here. So, for first instruction, that is I1 executing fetch, and then while executing execution part, so second instruction could execute the fetch and so on. So, this is one example of another example of pipeline execution when the instruction has only two phases, one is fetch, another is execute. Okay. What happens if you see the hardware organization? So, let us say there is a hardware which is responsible for instruction fetch, okay, and then another hardware that is responsible for execution. Execution must mostly happen in the ALU, because there you need to do some operation like addition or subtraction or any logical operation. Okay. So, now what happened in between, result is stored in a internal buffer. So, result will store, otherwise it will be overwritten. So, that is why you need the internal buffer in between the two hardware unit. Okay. This is very simple example, okay. But instruction stages, it is not only 2, there are 4 or 5 stages. Okay. For simplicity, we consider not 2, we will consider 4 stages. Okay. So, next we go. So, now we say instruction has 4 stages, one is fetch, another is decode, another is execute, and then write. Okay. Let us say I take one example, let us say add, let us say R1. So, we will add A, B and we will store to C. So, C equal to, basically I wanted to tell that C equal to A plus B. If we convert to the corresponding assembly language, so it will look like that. So, add A, comma B, comma C. So, these are the source. So, S1, S2 and this is the destination. You can do another way around, but here we are assuming source come first and then destination. So, do not deviate. Initially we have a story that is going on. Okay. So, do not think this is I am teaching something. Okay. So, its story is going on. Okay. So, here that is the C equal to A plus B. So, now what will happen, this instruction needs to be executed. So, it will go through 4 different stages or 4 different steps. So, first is fetch. What fetch? What is fetch? Fetch is like this instruction will be in the main memory. So, then we know that there is address bus and then CPU will place the address where this instruction is there, and this instruction address is nothing but the main memory. Okay. Even though we know there are presence of cache memory, but CPU will not have any idea. CPU will generate the address of main memory. Okay. So, therefore, so that is that entire fact, that is the bringing the data, or sorry, instruction or data, sorry, fetch means actually first part, fetch means actually it will bring the instruction. So, it will bring the data, sorry, it will bring the instruction from main memory or cache memory to the CPU. Entire fact is called the fetch. Bringing the instruction either from main memory or for cache memory to CPU is called the fetch. So, first page is fetch. Now, there will be a decoder, instruction decoder will decode it, it will understand what is this, means what the instruction is, whether it is a addition operation or subtraction operation or any other operation. So, it realizes, so this is a addition operation and it needs 2 operands. So, operands might be in the again main memory. So, therefore, it also bring the operand to CPU. So, everything included within the decode. So, in some book like Stallings, so the decoding is further divided into 2 parts. One is decode, that is decode means it will understand what is this instruction, and next it will fetch the operand. So, that is something called operand fetch. Okay. So, sometime it is said ki operand fetch. So, then decode sometime it is operand fetch plus decode. So, the number of stages will increase, main idea will remain same. Now execution, execution means actually that execution happen within the LU, because it is addition operation. So, we need to have the adder circuit. So, that is there in the ALU. Okay. So, after that results need to be stored in a variable C. Okay. So, that is something called is the write back. So, therefore, this is something called write. So, it will be written to the destination place, is fine. So, instruction fetch, that is fetch, then decode, decode includes the bringing the data from main memory or cache memory to the processor. So, that is decode, and then execute, execution happen within the LU, and then after that result need to be stored in a destination register or memory. So, that is something called write. So, now we will have the 4 stage. Okay. So, now if we have a 4 stage pipeline, how the scenario will be? It will be the remain same, only the diagram will have little change. So, first instruction it will go for fetch, decode, execute and write back. So, it will take 4 time units. So, after 4 time units only you will get one instruction. So, after 4 time units, every one cycle you will get one instruction, because when the first instruction was getting decoded, including the operand forwarding operand, bringing the operand from the main memory. So, second instruction started executing, it entered into the fetch phase. Okay. And if you see in the fourth, so 4 time, that 4 hardware units are really working simultaneously. One instruction is write back, another instruction is execution, another instruction is decode, another instruction is fetch. So, after 4 time unit is, you see that every one clock cycle will get one instruction will be executed. Okay. So, therefore, if you do not use the pipeline, the how many clock cycle it will be required. So, for each instruction it needs 4, and there are 4 instruction. So, it will take 16 cycle. Instead of that, say it will take, for first instruction it will take number of stages, that is 4, and then 1 is already gone, then 3. So, it will take 7 cycles. So, the hardware is, you can see this is the fetch unit, and whatever the results it will stored in an internal buffer, that is B1. Similarly, decode, it will store the result to B2, and execution unit is nothing but mostly ALU. Okay. And then B3 and then write back. So, results will be stored into the destination. There are some assumption I said, that each pipeline stage is expected to complete in 1 clock cycle. The clock period should be long enough to let the slowest pipeline stage to complete. This is also we said. Obviously, if there are mismatch in time between the 2 stages, obviously that faster will wait for the slower. Okay. Now, we will be talking about pipeline performance. Okay. So, potential increase in the performance resulting from pipeline is proportional to the number of pipeline stages. Now, we will be talking about the speed up factor of the pipeline processor. Okay. Now, what we said ki, yeah, there are 4 stages, and we can have the overlap between the operation. Now, and we have also seen with example, ki if you have pipeline and if you do not have pipeline, how much time it will take, right. So, in earlier example, we used to execute 4 instruction, and the pipeline has 4 stage. So, therefore, time taken was 4 into 4, so 16 cycle, otherwise it was 7 cycle. Okay. So, that we will generalize in the name of speed up factor. So, here we go. So, what I said ki, let us say tau is the time for each stage to complete each stage. So, we said we have a 4 stage. So, this is fetch, then we have decode. Okay. Let us say for each stage it takes tau cycle, right, tau I, and then there is intermediate buffer, it takes let us say di, or it is fixed for the all internal stage here. Now, if we wish to execute any instruction, okay, so how long time it will take? So, this is Ti, from starting from here to here, time will be Ti plus d. Similarly, starting from here to here, it will Ti plus d. Okay. Let us say for simplicity we consider, and then in general what happened, Ti is much higher than the d, delay within the internal buffer. And for to process from one so that means we are considering this one is tau. So, now we wish to execute n instruction. So, then how long time it will take? So, to execute n instruction, let us say time t n and k is the number of stage. Instead of considering the 4 stage, we consider that there are k stage. So, total time will be, if we use pipeline, what will be the total time? So, first instruction will take how long? It is the number of stage cycle, right. So, each you consider that is the number of stages into tau. Each stage takes tau unit time. So, number of stage is k. So, therefore, first cycle, first instruction will take k into tau, and then how many instruction left, that is n minus 1 into tau. Okay. It is the same thing. So, let us say in earlier example, so that is washer, dryer and the fold. How long it will take? So, just simply you add it, that is the first instruction. For next, it will take the maximum of this. So, this is k tau, and we consider that each stage take equal number of time. So, that is tau. So, this is k tau, and after the 4th cycle, in earlier example, every clock cycle will get one instruction. So, how many instruction left, that is n minus 1, and then clock period is tau. Instead of clock cycle, I am saying clock period tau. So, it will be the total time. Okay. So, if you do not use the pipeline, then what will be the time? So, without pipeline, what will be the time? Say T n. So, n into k into tau. So, earlier is like 1.5 into 4. So, that is 1.5 into 4, right. So, this is something like that, because each instruction will take k into tau, and there are n instructions. So, n into k into tau. Now, how much speed up we got if you use pipeline, if you do not use pipeline? Okay. So, what will be the speed up? So, that is the performance, pipeline performance. Okay. So, speed up will be here. If we use without pipelining, n into k into tau. Now, if we use pipeline or pipelined processor, then what will be the time? K into tau plus n minus 1 into tau. So, you can write n into k plus n minus 1. Now you divide by n. So, you will get k divided by k by n plus n minus 1 by n. So, now if you see n tends to infinity, that means instead of 4 instruction, if you have a huge number of instructions that in a processor, we do not know actually how many instruction will be there in a program. So, if n tends to infinity, then what will be the value here? So, this term will be 0, this will be close to 1 and this will be k. So, therefore, speed up factor will be k, right. So, if you use pipeline and if you compare with a processor without pipeline, so speed up will be k. What is k? K is the number of stages. So, therefore, if you go back here, there was something written, you see. Okay. This is pipelining performance, potential increase in performance resulting from pipeline is proportional to the number of pipeline stages. So, speed up factor will be k, but there are different assumptions. In between there should not be stop, there should be continuous stream of instruction. Okay. Those are the conditions. So, one has to study very consistently, otherwise pipeline will stop and then it will take more than 4 years. Yeah, that is underlined. It is proportional to the number of pipeline stages. So, now life is not so easy. So, therefore, you can see one example here. So, first instruction it went very smoothly. So, it took only 4 cycles. For the second guy, second instruction. Okay. So, what happened actually, he is taking or this instruction takes much longer time for execution unit. And what will affect for the subsequent guys? Okay. It is like a long queue in a hostel, right, in hall, and someone is taking rice. Okay. So, it will take long for it will have longer effect for the other guys. Okay. So, it is the same thing, because this instruction is taking for executing, it is taking much longer time. What may be the reason? Maybe the reason is addition is very simple, but let us say division operation. Okay. And you have seen that division operation in arithmetic is bit tricky than in other operation, right. I do not know how many of you understood division correctly. I taught, right? Don't tell. Huh? So, therefore, division operation it takes much longer time. So, therefore, it will take it may not be completed within one cycle. Okay. It will take another 2 more cycles. And what is the effect for other guys? So, other instruction will be stalled here. It cannot proceed, because that hardware unit, there is only one hardware unit that is being used by some other instruction. And what will happen for the subsequent instruction? You see, this is stalled, this is stalled. So, there is some disturb. For any kind of disturb, this you will not get the desired result. So, this will affect the pipeline performance also. And these may happen for different reasons. So, there are major 3 reasons for which pipeline can be stalled. Because what we learned, there is something called cache miss, right. So, if there is a cache miss, means instruction is not there in the cache, so it has to be brought from the main memory, because that is first part is the fetch. So, therefore, main memory it will take bringing data from the or instruction from the main memory will take much longer time. So, then pipeline will be stopped. So, this may be the one reason. So, initially it will be stopped instead of in between, and this is the reason I said ki it is not the addition operation, it is complex, the task is bit complex like division. So, it is taking much longer time. Not only that, so you put a statement if do not sleep. Okay. So, you put a statement that I greater than equal to 10, and then you do this operation, otherwise you do not do. So, it is not happening sequentially. If it does not happen sequentially, so there is jump instruction. So, jump means actually program counter value will change and then entire sequence will change. It was getting executed in the first portion, now it will execute with different portion. Program counter value will change and so many things happen. So, due to this one again that continuous stream of flow of instruction will not be there. And then another thing is something called data hazard, and these things are called the hazard, because pipeline stall for any reason, that is something called hazard, and there are 3 types of hazard. Okay. So, here the previous pipeline is said to have been stalled for 2 clock cycle, as you have seen. So, 2 clock cycle pipeline stalled. For any reason, if the pipeline is stalled, is called the hazard. Okay. So, here any condition that causes a pipeline to stall is called the hazard. Okay. So, one important is called data hazard. If there is a dependency between 2 instructions, then data hazard will happen. How that dependency? Now, let us say something like that. So, let us say A is B plus C, and now D is something A plus 10. You see, this first instruction has destination A, but same operand is there in the second instruction. So, there is a dependency between the first instruction and second instruction. If this kind of thing is there, so that is there will be some kind of hazard that I will explain next. I think same thing you must have studied up to some extent in case of the DBMS. So, I will explain it this one. Okay. So, what is data hazard? But there are other hazard, that is instruction hazard I already told, but this one will be again I will tell you in the class. So, there is something called structural hazard. So, just I wanted to show one example here. This is the example of data hazard. Okay. So, just quickly I will stop at a point, then next day I will start the same thing, but just to show what happened if there is some data hazard. Okay. Here I will explain this one, and that will be the end of today's class. Okay. So, what happened? There are 2 instructions, one is multiplication, another is addition, and there is a dependency between this part, like there is dependency. So, this is A 3 plus A and then B equal to 4 into A. So, there is a direct dependency, this is source and this is, so this is destination and this is source for this instruction. If there is this type of dependency is there between 2 consecutive instruction, if it is not consecutive, there is any problem. If there are dependency between 2 consecutive instruction, what will happen? You just see. I will explain in the next day here. So, we have the first instruction, no problem for first instruction, that is multiplication. So, it is executed up to W1. What will happen? So, after that when it decodes, it will realize that it has the operand, that is A, and A is already the destination of just previous instruction, and that computation is yet to complete, because this is execute not written back, that means result is not written to the destination. So, therefore, what will happen? The second instruction should wait until or unless it complete. So, after completion of that, it will fetch the data from the operand, that is A. So, this one unit cycle will be stalled, that pipeline will be stalled. Okay. So, I stop at this point. Okay. And as I said, you follow the book, that is Amateur. You can follow some other books like Patterson or other thing, but for initial stage this would be the good book for you. Okay. So, I stop here.